Yeah, okay. So then let's continue also here in life. I think I should think about a different opening sentence at some stage. But okay, so to summarize, what we did pretty much the last two lectures. So it was this derivation of the master equation. And okay, in part, I think it was a bit technical, some new concepts introduced. But the upshot, is really what's written more or less on the slide here, that we have quite generically a system coupled to an environment. Okay, environment is big, we couple into the environment. Then the density operator of the system will be described by this equation. So it has this usual commutator with the original Hamiltonian. That's our Schrödinger equation. There might be some corrections to this Hamiltonian. Very often we can frequency shifts or so. Very often we have to simply reabsorb this in the system evolution. But then there are kind of two new terms, okay, which I cannot write as a commutator. And these are always of the form some operator C rho C dagger minus C dagger C rho minus rho C dagger C, or the reverse process. And they have to do with the dissipative dynamics. So you emit excitation into the bath. It gets, they have this Markov approximation. So we excite the bath and it quickly dissipates. So therefore, all this information is lost. If we have a thermal bath, if you already have some excitation in the bath, we can also have the opposite process. So, you can not only emit photon in the bath, but also reabsorb it. Okay, this particularly if you, for example, go to a solid system, you're working with some spin defect in the solid, then it has low frequencies. At these frequencies, you have thermal phonons. So then kind of both of these processes will be relevant. And the other point is, okay, so what we really have, okay, this is the system evolution, and everything in this dissipation kind of depends. You can boil down to something. So the system's coupled to the bath, and what we're interested in, so this coupling is described by these collective operators, these collective bath operators that we find. And everything we're interested in is contained in the correlation functions. So what do these correlation functions mean? You create an excitation in the bath, and at a later time you look, is it still there? If this decays very fast, this means this excitation has dissipated. It's no longer accessible for the system. And therefore, we have this incoherent, this irreversible dissipative dynamics. Okay. And everything is so these are these correlation functions. So one for emission, one for absorption, and they are evaluated always at the characteristic frequency of the system. Okay. So therefore, you do this Fourier transform or Laplace transform. Yeah.
For the second term, for the absorption, how can I like understand the absorption? If there's always the CC dagger, how does the like where does it get absorbed from the bath?
So this corresponds. So maybe let's go then to the Tulavertum in two slides. So where we also had introduced this thermal excitation. So let me just maybe 1 second for this question. Yeah, so this is the general framework. We can then also say, okay, completely general, even if you don't know anything, to have kind of a equation, so time local equation for the density operator to ensure that it's positive and trace preserving, it actually has to be of this form. Okay, always there's a commutator with some Hamiltonian term, and then there are this dissipative term, which can now depend on different sums over jump operators. They can also look more complicated, but it always has to be of this form. Okay, so to ensure that what we get out is a valid density operator. We introduced this notation, short notation. Okay, it's a linear equation. So this is rho dot is some operator acting on rho. Okay, so this will be called now this Liouville super operator because it's an operator acting on the space of density matrices. Okay, but in principle, it's all a linear equation. And what we also showed is that if you have this equation for the density operator, you can convert it into an equation for the time derivative of observables by plugging in the definition of expectation value and then doing a little bit of cyclic permutations under the trace to get in this form. And then this is then easy to evaluate as we see now. If we now have, for example, a sigma minus operator here for decay, we evaluate the sigma z operator, then it's the commutator between sigma minus sigma z that appears here. So you can then just put in a few commutation relations to generate then the equation of motion for expectation values. And this is kind of what we what we then ended last yesterday. So then we say, okay, what now happens if I now do a two-level system coupled to a thermal reservoir? Okay, so we had the usual system Hamiltonian, that's some potential driving field with detuning, omega. And then we have these two processes. And I said the first one is, if I set the temperature to 0, the end thermal is 0. So this second line vanishes. And the first one, we just have this decay process. Okay, so and here we have, keep in mind this operator here, the first one that appears here, that's the jump operator. And that has to do, if I create an excitation in the bath, I apply this this operator to the system. Okay, I de-excite the system, create an excitation in the bath. But now if I have thermal processes, so this would be decay, but also if I have thermal excitation in the environment, I can absorb photons from the environment, and this would be then described by this process. Okay, so now I have, this would actually be, if I'm in the ground state, I act with sigma plus, I will be, we transition to the excited state. Okay, it's just a reverse process, and that's of course only possible if there's some energy in the bath that I can absorb. So, and we only restricted ourselves to thermal reservoirs, so therefore we have an N thermal here. And then the simplest type of calculation, does this now make sense? So let's assume there's no driving field, okay, just is going up and going down. And then we see that, so this sigma C, let's say if we look at the population inversion, so the sigma C operator. So first of all, we see that it decays if I have an initial, let's say, inverted state or also ground state. This guy quickly decays. So the hotter the temperature, so the reservoir, also the faster it decays. And this simply because you see that both processes are kind of stimulated. Okay, if there are already many excitations in the bath, also the system it's easier to emit into the bath if there are already excitations there. That's because we have this bosonic, this stimulated emission. So therefore, this decay process is enhanced, but also the excitation is enhanced. Okay, and both of them will actually contribute to a decay. So this process led a decay of the ground state population. This process leads to a decay of the excited state population. So if I look at the sigma C, the difference between them is just amplified by this sum. Okay, it's really scaled with 2n plus 1. But then you can also see, okay, what happens then? Okay, this relaxes. And if you look at the steady state, even without solving now this equation, if you look at the long time dynamics, this means the system relaxes to an equilibrium. This time derivative eventually will vanish. And then I just have to confine by setting this to 0. And then I can get also the equilibrium expectation value. You see from this result here for gamma, so it's just 1 over 2n thermal plus 1. And this I can, if I rewrite it a little bit, can write as a hyperbolic tangent of this ratio. And this is exactly the thermal equilibrium magnetization of a spin. If you go back to statistical physics, so you recover this equilibrium state. So maybe a small point here now. So this is, okay, I can show this for this example. We can also show it then for a harmonic oscillator for simple examples. So this is, in general, is not guaranteed, okay, that you reach equilibrium. So, and one thing which we discussed yesterday after lecture, so if you have some more complicated atomic system, okay, so you have a lot of, for example, ground states, and the excited state is coupled to a thermal reservoir, but the ground states are kind of, because they're so weakly coupled, they are unaffected. Okay, in this case, you can have that, then you have simply a few states which are not affected by these jump processes. Okay, so therefore they will also not evolve. And then depending on the state I have initially, I will not naturally evolve to something that is exact thermal equilibrium state. Okay, so I mean, if my coupling to the environment is complicated enough, so all transitions are somehow possible, all states are somehow connected to a thermal reservoir, then of course we, expect also from statistical physics that I reach a thermal state, but it can generate a lot of situations where this is actually not the case. You can have symmetries, you have decoupled subspaces, you can have more complicated ways to engineer your coupling to the bath, okay, so that this is not guaranteed, but at least if you have simple system, it turns out to be consistent. Okay, yeah. So this was a bit the starting point, and let's okay, two-level system. This was now undriven, so no driving field, and just coupling to a thermal reservoir. So let's also just briefly go through some other possibilities that we have. So what happens if we add dephasing? So this means my jump operator, in this case, the C operator is it's not sigma plus or sigma minus, it's the sigma C, okay, essentially the energy difference that is now coupling to the reservoir. Okay, so this means the energy difference, this is now affected by the reservoirs, it's essentially fluctuating. And if I do simply put this now, substitute this in my general form, I will get a term like this. So this, in this case, C is also is Hermitian, so C dagger is C. So I have 2 sigma z rho sigma z, and then minus sigma z squared rho minus rho sigma z squared. Okay, and you can also realize that sigma z squared would be identity. Okay, so you can even simplify this. Okay, so this looks now a little bit different than what we had before. So what is the effect of such a master term in my master equation? So let's again do the expectation values. If I now look at the population difference, the evolution of sigma C operator, I plug it in. Remember, we had these general commutators. Now my C and C dagger are both the sigma Z operator. So if I look at the evolution of sigma Z, I get this commutator, this vanishes, and therefore these terms, obviously, I mean, there's no exchange of population, so therefore they also don't affect the population. Okay, but if I have now my sigma minus operator, I plug it in. Okay, there's the Hamiltonian evolution. If I put in some delta, that's what you already know. And then from this term, I get this commutator, sigma minus, sigma z. So this commutator is again just 2 times sigma minus. Again, sigma minus over here. Okay, so all these terms are proportional to sigma minus. And then including this factor 4, that's why I defined this rate in this way, will then give me in total so that 2 times sigma minus and then another 2 times sigma minus. And overall, I get then the Baire evolution with the tuning and then minus gamma sigma minus. Okay, so this term, they don't do anything to the population, but they would change the expectation value of the coherences. Okay, so therefore it's called dephasing, decoherence mechanisms. So they affect the off-diagonal elements. And if we just now look at the coherence, so we said coherence is roughly the average dipole moment that we have in the system. And then we simply see if everything is without the environment, it would just sigma minus would just oscillate with this detuning. And because we have now this dephasing term, it will also decay with this rate gamma phi. Okay, so this term in the master equation would translate into a decay of coherences, but it will not affect the populations. And yeah, and this one remark, I mean, this is also what we briefly pointed out in one of the first sections. So this type of term, it models a dephasing process, but very often actually find if you have slowly fluctuating fields in the environment, then it's actually this master equation might not always be very correct. Because here we assume, in our derivation, we go back, we assume that this correlation environment forgets quickly, it's Markovian. So therefore, if I have something that is slowly varying fields, then this would not be a good approximation. But, if I don't know anything else, and I just see, okay, in my experiments, I have something, my population stays the same for a long time, but I see the losses in the coherences. If I try to also drive it with a Rabi frequency, there's loss of coherence. This would be a good choice to put it in your model and at least get a rough idea about this effect. Okay, and now then we can put everything together, and I think this is now not, so going back to our Bloch equations that we had in the beginning of the lecture, there we said, okay, we want to have a 2-level atom. We thought about optical systems, so there's temperature equals 0, but we had a decay channel and we had a dephasing channel, and now you can simply put everything together, and I think I will not go now through these calculations, so you work out all these commutators, by itself, and then you find an equation for the sigma minus operator. The sigma plus operator is, of course, just the complex conjugate of this guy. And if I do the sigma z operator, so you see there's the dynamics with the coherent, the driving field, the detuning, and now we have this additional contributions from dissipation. So in the sigma minus, we have both the decay term and this dephasing term. And for the sigma z operator, we only have the decay term that contributes. And this last point, okay, I can rewrite this, the excited state population. I can rewrite in terms of sigma z plus 1, and therefore we get this type of equation. And if you put everything together again, I mean, go through it, but it's all just accommodators with Pauli operators. And if we put then everything together, we can summarize the equation for sigma minus, sigma plus, sigma c, and we can again write this in this matrix form plus this offset vector. And then you see, if you look, compare this matrix to what we had in section 1.5 or so, you see we get exactly the same result. Okay, so back then we did a little bit of arguing how these terms should look like, but this Bloch equation now really come out of such a general master equation formulas. Okay, anything on this? On this part. So because I think before now continue with the other example, harmonic oscillator, I actually would like to stop share here and just briefly talk us about numerics, because this will be then relevant for the exercises. Let me so these are these quantum optics with Python nodes that you can find on the Moodle system. And so let me just go a little bit through the main ideas, how we actually, if we want to simulate such a master equation. Okay, so I told you that this is a linear equation. So we can somehow, if it's a linear equation, we can always convert it into matrix times vector multiplication. Okay, but if you now want to do it, okay, you have to think of a little bit about how you would actually implement it. And of course, not a unique way, but therefore, at some stage you have to fix how you do this transformation from density operators into vectors and so on. And I just briefly want to go through. Okay, so the main thing is that we're looking at the density operator. That's an operator. If you express it in some basis, it's essentially a matrix. And the first thing, I have my system of interest, and the first thing I do is I choose a basis state. Okay, it can be EG for a two-level system, or the number states for harmonic oscillator. And if I write then this is a matrix, okay, expressed in a basis, I can write it in terms of these matrix elements. And now so very often we think about the density operator as matrix, but of course, if I have something like this rho, let's write it as G, rho EG, rho GE, rho GG. Okay, so this would be a typical 2x2 density operator. But of course, I can always write this in the form, I can just take all these elements and group them in the vector. Okay, so this would be GG, rho EG. And now I have to see if I do it correctly here. So it's the other way around. GE, EG, and rho EE. Okay, so these are linear systems. So specifying these elements of this vector, these are my basis operators. I'm living in a space of operators. So all these projection on LK are a complete set of my operator space. Okay, so with having this combination, I can construct any operator in this subspace. Okay, so and then you see, so you can take these matrix elements and write them in a vector. And of course, you have to specify whether you first, you do it essentially along this line or along this line. And here in my notes, okay, I do consistently where it's always first I change the second index and then I change the first index. Okay, so so in the following, we want to work with this vector representation of density matrices. And then, you can think about, okay, so what is now density operator that's a projector on the state psi? Suppose I have already a state psi given, then you essentially see, okay, with a certain, so I have now my psi is also sum over k, ck, and these basis vectors. And then my density operator, psi, the sum over k, L, ck, cl star, kl. Okay, so therefore I know my matrix elements. So these are my row kl elements. And then if you keep track of the indices and try it out once or twice, then you see that if I have now my vector given, in Python, for example, as a vector of these coefficients of psi, then I take this Kronecker tensor product. The second one, I take the complex conjugate, but I simply stick them together like this. I get exactly the form of the density operator here. Okay, so you can just, if I have these coefficients given, I take this tensor product, and then I get a vector, column vector that has then the correct entries here. Okay, this is nothing complicated, but one has to try it out to get the right combination here. But otherwise, yeah, this can be done. And just also think about with this. So if at some stage you have this row in this vector form, you want to get the matrix representation back, you can simply reshape this into T times D matrix again. Or if at some stage I give you a density operator in matrix form, you can also just flatten it to get the correct vector representation.
So this indices, that's also the standard way NumPy does it then.
So with this, so what you, I mean, at some stage you have to fix this this convention here, and then so these type of comments, let's say in this order, I do it here, it will be consistent with the notation I use in this script. Yeah. Yeah. So I think it's then more or less adapted to the convention that is also used in NumPy. Yeah, but I mean, the best thing is always to first use a small short example and show that everything is consistent. Yeah. Okay. So now I think the next thing is to do, okay, so what I have in my Liouville operator, is I have this jump operator acting on row. Okay, so I have here a matrix multiplication, and this will give me now a new. Okay, so this is my master equation, so this will give me kind of a new operator. I apply the jump operator with the density operator, this gives me a new operator. Okay, so and now it's okay. Usually if we work with matrix representation to get the new operator, we simply do a matrix multiplication like this. Okay, we take the two matrix representation, multiply them together. And now we want to actually get we're starting here with a vector. Let's call it like this, rho prime, and we want to now get and we put in here a vector. Okay, so we want to get a vector out. So we want to put in vector rho and get a new vector out. Okay. So you see, first of all, so the object that we have here, that's of course a linear relation. So this must be a matrix. So how do I get this matrix? And this is, again, now you have to go through at some stage through all these indices. But you see, you put in this operator representation, you multiply out. So here you get then a delta function. And in the end, this is the matrix multiplication that you get. Okay. And then these elements are again the elements of your new density operator. Okay, that are here. So now I want to write everything in kind of a matrix multiplication. So this is a matrix multiplication, and I want to write it as a matrix multiplied by vector. Okay, and if you kind of see, I mean, very roughly what's going on, you already see here. So the original elements, row nm. So the index m is not affected here because I multiply this matrix here from the left. Okay, so the only thing is I change the indices, the first index row n will change. Okay, so therefore also in this vector representation, the first entries, they will be mixed up, but the second ones will essentially stay the same. And if you then think about it, how do I realize this? Then you find, okay, if I now take my matrix representation of A and do a tensor product with the identity, then this will give me now a bigger matrix that only changes kind of the first indices, but leaves the other one the same. Okay, so with this, in this representation, the action of an operator A acting on this row matrix is equivalent to a linear operation. A linear operation I can always represent as a matrix, but of course this matrix now lives in a bigger space, okay? Because my vector row, just go back. I mean, if I look, I'm working in a d-dimensional system, then this vector is d squared, has now d squared elements. So also this operator here must have in total d squared, is a matrix that is d squared times d squared. And you see, I mean, this is the individual matrix. So if I make this tensor product, I exactly get what I want. Okay, again, it's nothing complicated here. It's just about writing out these indices and making sure that kind of this matrix that you put in here kind of gives you, if you work it out, it will give you kind of exactly the same type of summation over here. Okay, so this would be the case if you do the A operating here from the left. But then you can also have another case where you have the A operator, the jump operator acting on row from the other side. Okay, now you write out these equations and it looks all very similar, but now you see that somehow instead of the n's are summed over, here you sum over m, so you sum over the second index. Okay, so these matrix elements are now in different positions, but okay, once you understood this one, okay, you can actually try it out a little bit and play around, and then you find that the corresponding super operator here is now the tensor product of one of the identity, and now with this operator, the transpose. Okay, it's not the Hermitian Hermitian complex, it's the transpose. Okay, simply because here these elements, here you sum over this index n, here you sum over the other index m, so therefore we first have to transpose it, and the corresponding operator is like that. Okay, so again, it's principle everything linear algebra. We have our, so we have some object that in this case, an operator, we represent it in some basis. The basis elements are these projection K and L. That's my basis, and everything are the coefficients. So now I can represent this operator as a vector with all these coefficients. And then I do these operations, I multiply this operator with another matrix, and this is a linear operation. Okay, so it will change from the original set of vectors. I will get a new vector which has different coefficients. And to get from the first side, I mean, everything is linear. So therefore, if I multiply the first vector with some matrix, I will get the correct coefficients. And then how to identify this? Yeah, I work out this matrix multiplication and play a little bit around with arranging everything. And then I find the super operator is is either A, tensor identity from left multiplication, and if I have a right multiplication, it's identity tensor, the transpose of this matrix. And then you can say, okay, so I also have situations in my master equation where I even have so rho prime equals C rho C dagger. This, then I have an operator from this side and from the other side. But here you can realize that such a situation is just, okay, I apply first the B operator from one side, from the right here, and then I act with A from the other side. So therefore, this is only, I first apply this right multiplication, and then I apply the left multiplication. And you see, because here we have 1 tensor A, and here we have A tensor 1. So this combination, we can apply these matrices one after the other. But because they are this tensor product structure with identity, we can also just have A. So this combination A rho B would translate over into A tensor B transpose. Yeah.
Maybe a stupid question, but why we do this? Like, why is the vector representation more useful than the matrix representation, or is it, or like, is there a specific purpose when it's necessary?
There is, so I mean, once you have done, so a lot of the things you can also do just doing matrix multiplications. But let's say in this form, we have then mapped our master equation and so on onto matrix time vector multiplication. So we have the typical linear system. And if you then calculate, let's say, a steady state or so, it's a matrix inversion or calculating eigenvalues of matrices. So it's in principle, everything is equivalent, yeah, and you have to do the same number of multiplications in the computer then, yeah, because everything is equivalent. But in this way, yeah, we have this structure. Then Liouville operator will be a matrix, and then we can use all the standard routines for linear algebra. I think this. So. Yeah, and again, this is about always keeping track of the ordering here, but you see these operations are then translate in just this Kronecker, these tensor products here acting on multiplying on rho. One thing, okay, so in this formalism, so something that you might want to evaluate. So given now this density operator, okay, we want to evaluate expectation values. And what you see, what we usually do is we take the trace of operator A times rho. Okay, so this product we already know in this vector representation. Now this becomes the super operator. But now we have, okay, we multiply this, we get a rho prime. And now we want to take the trace. Okay, and trace is usually defined for matrices. But how do we, what does it actually mean, the trace? Let's go back to this example here. We have, okay, taking out of these elements, we want to take the trace. So we only want to take the diagonal elements. In this case would be rho GG, and in this case would be rho EE. And in general, if you have these matrices, so I'm taking the trace of my rho would correspond to sum over I, rho I. So we only want the diagonal elements. So now if you go back to this this representation that we had above. Okay, so how do I pick? I give you this vector. How do I get all the diagonal elements and sum over them? You know, you see, okay, I certainly take the first one, and then I have, you know, it's not written here, but here there would be an no, so then I go, so you have 1, 1, 1. The next one would be actually this rho to do sitting over here. So then you see between this one and this element, they're in total D. So going from 2 to D, and then the next one, they're in total D elements. Okay. So if I want to now collect all the diagonal elements, I have to take the first one. Then I have to, all the rest I multiply with 0. So D times 0. Then I take this one. Then I again have D elements which I don't care, and so on. So you can therefore take this trace, okay, so you can construct your vector that has exactly these ones and zeros, okay? A 1, then d times zeros, then again a 1, d times 0, then again a 1, this. So if I take this row vector now and multiply this with my density operator, I will exactly pick out all the diagonal elements and sum them up by doing this multiplication. Okay, so the trace, taking the trace in this case can be implemented by also kind of this linear transformation by multiplying with a vector of this type. And this is also, yeah, so then taking an expectation value, in this case, it would just look like that, okay? A expectation value is trace over this. So I have my density operator in vector form. I apply the A operator from the left. So therefore I multiply it with this A tensor identity. So this big super operator, this gives me again now a vector. And this vector, column vector, I multiply with this trace vector, this is a row vector. And that gives me then one number. And that's exactly the trace of this object. Okay, and the interesting, if you then go to Python and think a little bit how these things are implemented, you see that this vector over here, it's nothing else but 1 0 0 0 0 1 0 0 0, then the next line 0 1 0 0 0. So it's actually an identity matrix that I stretched out. Okay, so therefore you can simply you take the identity, so this is a d-dimensional Hilbert space, you take the identity matrix, you flatten it out, and this exactly produces you this vector I just constructed. Yeah? And then take an expectation value, I have my density operator, I have this left operation with A, that gives a big matrix, I apply it, and then I multiply it with this trace vector, and I get the expectation value. Okay, so this is then very, very convenient in this representation. Okay, and that's already then some of the main ingredients we need. So now let's go back, apply this to our master equation, so that you see that in the end this thing. So once you have thought about a little bit how to about all these indices, everything else is then very simple. So we have our master equation. The derivative of this density operator is the super operator L, Liouville operator acting in row, and we want to convert this into a vector times matrix equation. Okay, so now this L, this Roman L here is now a big matrix. So how do I now get this matrix, this d squared times d squared dimensional matrix? For example, in my master equation, I have this commutator with Hamiltonian. This is H acting from the left minus H acting from the right. So I do this translation rules from before. H tensor 1 is the left operation, 1 tensor H transpose. I mean, usually transpose. Yeah, now okay, I need to take the transpose, so it's not a Hermitian conjugate. Be aware of this. From the other side, and then this super operator, this big matrix now would correspond to a commutator with H. And similar, I have these type of dissipation terms. Okay, it's always C rho C dagger, C dagger C rho, and so on. And this just translates, as we discussed previously, C tensor C dagger. Again, don't forget about the transpose here, and make the distinction between dagger and transpose. And yeah, and here it's from this side, and here's from the other side. Okay, and once I have this equation, I have the same as the Schrödinger equation. Okay, I have a vector. Vector dot is matrix times vector. So here I can just do the same. If I want to solve the time dynamics, I just do the same, solve in the initial value problem or so. I have this linear equation. I can just apply all these things. And yeah, and here in this example, I mean, there's we can now go, for example, to our James Cummings model. So just very briefly, James Cummings model. Now I have a two-level atom. I have a cavity and a coupling between them. And my master equation, I have a decay channel for my atom. Okay, it's jump operator sigma minus, and I have a decay of my cavity. That is a jump operator A. So this, okay, we did discuss it then a little bit later. And okay, so now this is my thing. I want to solve it. And kind of the Python code would then, I mean, please take a look at it and try it out. So it's very, in principle, then very simple. You construct, so this is a sigma minus operator, sigma plus operator that we need. We need this, the A and the A dagger operator. So that's, we had already before. We need a few, all these identity matrices, just to keep track of them. And then there is a atomic part of the Hamiltonian, okay, acting on, just on the atom part. There's one part just acting on the system, on the cavity part. And then there's this coupling, and the coupling, okay, lives in the combined space. So I do sigma minus operator, tensor, A dagger operator, and so on. Okay, so this is the Hamiltonian part that we already had in the exercise from before. And then, okay, if I do now my full Hamiltonian, just make sure that this operator here is defined only in the atom space. So therefore I so here, so this is the atom Hamiltonian, and therefore I then take the tensor product with the identity on the cavity space. Okay, so at this stage, everything is what we already had. Okay, so we have the total Hamiltonian of the system, and now I construct the density operator out of this. So I simply take this my Hamiltonian, and then I do this tensor product H with identity minus the other way around, okay, identity and H transpose. Maybe keep in mind, so here I always have this, not the NumPy Kronecker, but the SciPy sparse Kronecker. The thing is that, especially if you work with harmonic oscillators and so on, you start with a large Hilbert space, and all the super operators are the dimension squared. Okay, so it's with this master equation, you very easily run into huge matrices. And therefore, you want to define everything here as sparse matrices. I mean, there will be a lot of zeros and so on. So therefore, you win a lot if you define everything in sparse matrices. If you don't do this, you're having one harmonic oscillator, density operator, you very quickly run out of memory. Okay, so this would be the Hamiltonian part. And then okay, what about the other two terms? Now I have to, for example, implement this guy over here. So gamma over 2, and then this combination, sigma minus rho, sigma plus, and these other combined terms. And here it's simply, use this prescription that we had before. So it's all about ordering, but you see, you need, okay, so first, this is the sigma minus operator, first generalized from this subspace of the atom to the full Hilbert space. Okay, so I do this here. And then with this outer Kronecker delta, okay, I essentially implement this C rho, C dagger super operator. So, but I mean, once you have this ordering, if you have any other term, so any other master equation, okay, so you just copy and paste this line and then plug in the corresponding jump operators. And then, okay, so once after that, the full Liouville matrix is the Hamiltonian part, the gamma, the decay of the atom, and the decay of the cavity. And and this was also then, okay, in this example, then you look at the initial state. You have a psi 0 that you construct, okay, it's the ground state times, in this case, it's a coherent state. You construct the density operator by just taking this tensor product. Then you have your initial state, and everything else is just, we define a time derivative. We do solve IVB, and we get now a set of density matrices out at different times. And then we do these expectation values. We don't want the density operator. We usually want the expectation values. And you see, construct the operators of interest. For example, the excited the cavity occupation number or something, or the excited state population. Again, we build all the operators in the full Hilbert space. And then we apply this prescription. We take the rho of t, we multiply it by the super operator, and then we take the trace of it, and this gives me then the corresponding results. Okay, so you need to, probably once go through this. There's also now, this week, I think I put a small master equation tutorial. So first of all, look at this example. There's another Python file on Moodle, on master equation tutorial, a little bit going again through all the relevant steps. Go through this, but once you have a few of these basic rules, it's always copy and paste of these few lines, and then you can construct arbitrary master equations and then solve them and calculate expectation values. Okay, one point here I also want to make. Okay, so this is about doing time evolution that we need a lot. What we also need a lot is the steady state. Okay, so we time evolve it, and usually if you have some relaxation, the system relaxes into a steady state. Okay, at some stage it doesn't change anymore. And this we want, okay, steady state is then defined as when the time derivative goes to 0. Okay, at long times it will time derivative goes 0. And if I translate this into my matrix vector representation, I see that this corresponds to the steady state. Is essentially the 0. So L, the super operator applied to the steady state, gives me 0. Okay, so therefore I have to this now. So I essentially have to find the null space. If you think about linear algebra, this means I have to find the null space, or you can think about this row 0 has a 0 eigenvalue. Okay, it's the 0 eigenvalue of this super operator L here. Okay, so with let me see, so in principle, if you have small systems, there is, for example, this sci-fi linear null space routine that gives you now this 0 eigen this vector directly. Very often, this is not very. So I think this is for full matrices of full solution. So usually it's better to look for the 0 eigenvalue. Okay, so you can take this L, you can take the eigenvalues and take the 0 eigenvalue. So this would be this NumPy function linear eig. But then, as I already mentioned before, very often you deal with systems that are very huge. Okay, so you use sparse matrices, and you don't want to diagonalize the whole matrix, because that's also not what you want. You want the 0 eigenvalue. Okay, so what you then do in practice is you go to the sparse package. So you have your L is defined as a sparse matrix, and you calculate one of the eigenvalues that is closest to 0. Okay, that's what this comment does. Because these routines, these codes, I mean, they can calculate a few eigenvalues very efficiently, but they cannot produce the whole spectrum. It's also not needed. So you want this one eigenvalue. One important thing is then that these type of, also if you go to other programming languages, so these eigenvalues, I'm actually not sure how this routine, the sparse linear eigs does it, but usually if you calculate an eigenvalue of a matrix, you get back a normalized eigenvector. Okay, but what does it mean, normalized eigenvector? This is usually the vector norm. Okay, all the matrix elements squared added together. But actually here with my density operator, I don't want all these elements squared adding up to 1. I only want that the trace is 1. Okay, this element plus this element must be 1. Okay, so if you calculate an eigenvector, so quite generally, it will give you the wrong normalization back. Okay, so therefore, very importantly, I take 0 eigenvalue vector and then divide it by the trace of this value to get a normalized steady state back. Okay, so and that's usually how you then calculate the steady states using this eigs. So looking for the eigenvalues, and don't forget about the normalization here. So one final aspect, maybe one statement about this. So that's the usual routine. one thing that we already discussed with the Bloch equations. Yeah, so rho, let's say with the Bloch equations, we had rho EG. Let's call it like this. Okay, so the yeah, let's put it like this, GG. E dot equals. So if you convert, again, we do this for a two-level system, it has the dimension of 2. Density operator has 4 elements. So therefore, our Liouvillean, if I write it in this form, would be 4 times 4 matrix. So, but now we can have this matrix and it would look like this, vector times matrix equal vector, and therefore the steady state in this equation is actually the null space or the zero eigenvalue of this element. But what we also found is that most of the time we wrote our Bloch equation actually in this Bloch vector formalism, which had this form. Okay, so it's actually not a linear equation because it had this offset and it only had 3 elements. And the reason, of course, is that in this equation, we have the trace condition. So we have 4 equations, but actually the rho EE and the rho GG, they're not independent of each other. So in principle, what we do here in this formalism, there's always one equation that we don't need. Okay, we have huge matrix, but there's one equation that we don't need. And this you can actually use to kind of rewrite. I mean, this is a generic, okay, of this type of equation, but because we have this trace condition, you can express the last element of your density operator as 1 minus the sum over all the other diagonal elements. Okay, and if you do this, and maybe you can, without all the details, but you can imagine, okay, so then you get a new operator, which I call mu. Okay, so here I simply remove the last element. And this then obeys kind of this equation. Okay, so it's mu dot is some smaller matrix. I mean, it's only one line that I cut, okay, times mu. But there's also an offset. Okay, so this is now so these elements, okay, they depend on the last element, and this last element is then 1 minus these other elements. Okay, so you see from substituting this, I actually get this linear equation back, but I also get some offset terms. So it's more like we have for the Bloch vector over there. And this type of equation, and now it looks the following. So it's no longer the null space that I want to solve, but this is a matrix times this vector equals this offset vector. Okay, so it's of the form A matrix times this mu equals some, let's call it also this vector R. Okay, so this is another type of linear problem. Okay, so I have to find a solution of this general equation. So that's linear algebra to find a solution. So in general, this would be mu equals A minus 1. So the inverse of this matrix. But it turns out that this type of equations, they're also efficient algorithms. Okay, so this is a built-in function that is very efficient. And in what the end do is then this kind of applying the solve algorithm, the solve routine, which essentially solves you exactly this type of equation. Okay, so and with this is another way to get to avoid, let's say, the eigenvalue problem, but to get also directly out then the density operator. So first of all the mu, and then you stick this last component back in. So yeah, so I just wanted to point it out because it turns out also if you then look a little bit at this, so it's not always the case, but for many systems actually this is even slightly faster than the other methods. And again, don't worry about the details. You can actually in principle get this code here, and this would, then implement this calculating a steady state. So far, the most efficient way that I could put together myself. Okay, so this was a bit also explanation of these nodes, and this is maybe one final aspect of the spectrum. We only come back later. Some things that if you follow this type of approach, you have to be a little bit careful about ordering. So what we also did in the previous example, so we have, for example, multiple subsystems. Okay, so each of the subsystems can be now in a vector. And okay, this gives me this combined vector. So first make the tensor product of the individual states. So this would be the combined state then. And then I take the combined state and convert it into a density operator. So this is one way to do it, but you could also say, okay, what I do is first I take the subsystem 1 and I calculate my density operator rho 1, then I calculate rho 2, and then make the tensor product. And this will give you different, will in general give you different results. Okay, so just be aware of it. So you have to focus on, let's say, have one routine. And so this way of doing it, so first you construct the vector and then you convert them into density matrices, is different to first get the individual density operators and then put the tensor product together. So maybe for this lecture, it might not occur very often, but please be aware. And and also maybe I don't want to go through it right now, but also with super operators and so on. I mean, one has to be aware of these details. But maybe let's also tracing out and so on. So look at the nodes if you then want to really work with multiple subsystems. Look at the reduced density operators. It's not complicated, but at some stage one has to sit down and make sure that all the processes are done in the right ordering. Okay, but in principle, if you just take this so it can look at the steady state, so either do it like this or with this eigenvalue spectrum, that's the way how to calculate steady states, and look at this example with the dissipative James-Cummings Hamiltonian as for orientation if you then want to implement these master equations. Is there some immediate questions? Otherwise, there will be in the next exercises. Okay, there will be a small 3-level system, and then we will use this now more and more often. Okay, so then we can go back to the lecture. And actually continue just also briefly with this the second example. So we had this 2-level atom. Okay, another relevant case is that of harmonic oscillator. So let's go back to our example of a KVD mode, quantized system. We have a large mode spacings. We can approximately represent the field here by a single KVD mode. Typical frequency omega 0, omega c, which I call it here, omega 0, the mode operator A. And this is coupled, I can think about the mirror, that's some dielectric, but the field, I mean, hitting this mirror, okay, most of it will be reflected, but there will always be a small evanescent part that actually goes through the mirror, okay? So in this part will then couple to the field outside, and outside I have no constraint, I have no mirrors, okay? So here the photons actually form a very dense mode spacing, okay? So I have a single mode, essentially a single mode, and here I have a lot of modes. And I can also think about then the environment. Okay, it can be, as we had also last time, okay, it can be this quantized field of this environment. Plus, I can also have a classical part of my electric field that could be, for example, come from the laser. Okay, and yeah, if you think about it, I mean, it's of course the model now, the full mirror and really work out all the details can be very complicated. But how can I roughly understand? I mean, what would be the interaction with the environment be? So yeah, think about here the mirror. The ideal mirror means that the cavity field is really confined to this region and the environment is confined to the other region in space. If I now do a realistic system, then I have something like, at least some evanescent field, okay, that's leaking through the mirror. And there will be, in general, there will be now some region where the mode functions of the cavity field and the environment overlap. Okay, and if I go back to my my Hamiltonian, what is the so how can I construct an interaction Hamiltonian? So in this region, think about so my energy. Okay, I mean there might be some dielectric as well, but my energy is essentially given by energy density of electric field is E squared. Okay, so if I now take my E, and that's right, there's the cavity part plus the environment part, and multiply it out, there might be some small correction on the cavity side, but these are really tiny, some small correction on the environment side, but there will be a cross term E cavity field times the environment. Okay, so this will be kind of the minimal type of coupling, even though the details can be more complicated, but we expect something where there's a field interaction here. Okay. And now, of course, each of the fields I can quantize that the cavity field is A plus A dagger, and the environment is sum over all K modes, A plus AK plus AK dagger. Okay, so this would be the environment field. I mean, the laser component, the classical part, and then there will be something 0-point field, some strength here, but it will be something proportional AK plus AK dagger. Okay, so therefore, even without now making a detailed model, so if I plug this in, I see there's a classical term that will couple now to my cavity field. Okay, so keep in mind there's a so the cavity is also proportional to A plus A dagger. And okay, so I just show that here I changed the notation, show that this should be the BK should be the same here. Okay, so the cavity field is this, the environment field is the sum over K, BK plus BK dagger. You multiply these together. And one thing that we then always assume, we assume that we are looking at optical frequencies or something like this. The coupling is small. So therefore, I do a rotating wave approximation, and I only keep terms that are kind of energy conserving. Okay, so this would say, if I model decay of a cavity field, approximately this would be my system environment interaction of this type. Okay, I mean, this doesn't tell me what is this coupling strength here, and so on. Okay, but I can just now use this as a parameter, and later on I do my model, and then I measure it in the experiments. Okay, but it will be of this type. And now for our general type of analysis that we did, okay, so there is now this something that doesn't involve any quantized environment operators anymore. So this part I simply include into my system Hamiltonian. Okay, now I have the cavity, the harmonic oscillator, and the driving field that is the classical part from outside. And then all the rest here that is now in my interaction. So I can identify the jump operator. So the C operator, the system operator here is A. And the coupling is simply a sum over all these environment modes with some coupling constant G out front. Okay, so simple meaning, I mean, we have here the usual situation that the path is a bunch of harmonic oscillators. And from this type of interaction, we also see that the way the cavity couples to the environment will be proportional to A. Okay, so it's not A dagger A, or also because of the rotating wave approximation, we don't expect here an A dagger. So this would be the natural identification. So, and now, okay, once I have, okay, this is my system path interaction. It should be of this type. I don't know the details, but I can now immediately write down my master equation. Okay, it will look like that. It will have this Hamiltonian evolution with this classical driving field. And it will have now two terms. Okay, my environment can again be in a thermal state or can be in vacuum, but the jump operator is A, so I have an A rho A dagger contribution and the rest. And there's if it's in a thermal state, then I have also an A dagger rho A from the other side. And there's now a coupling constant or a decay rate gamma out in front. That depends on the properties of my mirrors. You know, now the detail of this interaction, this usually I don't know. But this rate gamma, you know, that I can then measure in experiments. Okay, so this would be the generic form for a master equation for harmonic oscillator, also in other settings. Okay, this whenever you have kind of or if you have a real moving particle, as long as the position is coupled to some displacement fields of phononic displacement fields or so, it would always be like this linear coupling, A dagger B, B dagger A, and then the master equation look the same. Okay, let's see what this master equation actually does. Okay, it looks complicated always, but let's use it now to evaluate terms or observables. And the first thing is to evaluate the field amplitude in the cavity. Okay, the expectation value of A. That's the simplest variable I can have. I use my formula from above. Okay, so first of all, the A expectation value rotates with the Bayer frequency. That's what you know. And from this driving field, if you go back here, so we have a part in the Hamiltonian that is proportional to A dagger. And if I take the commutator between A dagger and A, I get a number. Okay, I get this value back. So this gives me a constant driving field. I think we had this in the discussion of the harmonic oscillator and the brilliant states. So this will be this constant driving field, Bayer oscillation, constant driving field, everything coming from the Hamiltonian. Now I take these two parts and plug in this formula for the expectation values. Okay, so then I see again there are some commutators, some of them will vanish, and some of them will give me, in this case, -1, and so this vanish, and this gives me a +1. Okay, so this is gone, this is gone. Here I get a -1, and here I get a +1, and what's left with is so -1 times the expectation of A, and a +1 times the expectation value of A. Okay, so these contributions, this comes with a -1, this comes with a +1. So, for example, this n-thermal term cancels out, and we get actually quite a simple result. We get the amplitude. It will oscillate with this frequency. It will decay with the rate gamma over 2, and it will be driven from outside by the laser field. Okay, so, and maybe the important point here is that this classical field, let's say the average field, does actually not care about the thermal population. Okay, so, and this is maybe expected, you know, so the expectation value of A, that's kind of the average, the classical field. If you have a classical harmonic oscillator, even if it's coupled to a thermal reservoir, to a first approximation, so the mean amplitude will be just given by the external driving field and will respond to this driving field, but the mean value will not be affected by thermal fluctuations. And also this comes out here, because of these terms. Okay, and yeah, and then you can integrate this. This is the solution. Yeah, so what I maybe want to say here, okay, is so first of all, you can integrate it. Again, it's this linear equation that we had already a few times. You can also, and for this, you can go back. So you can immediately also see the steady state. I take this to, okay, I have to be careful. Just wanted to say I can set this to 0. So this is not possible because here you have a time-dependent driving field. Okay, keep in mind it's time-dependent. So in this case, we look at the full equation. It's the full solution for large times. The initial state, of course, is gone because I have a damping rate, and then I have to evaluate this integral. Okay, this is a simple exponential. And here you see you have omega 0 and the omega laser driving field, so they cancel each other. So let's take this integral from 0 to infinity and evaluate it. And then we get the steady state amplitude. And yeah, it's two things I want to emphasize here. Okay, so you have this harmonic oscillator, you drive it from outside, and the field, I mean, that's a general feature. Okay, it's a linear system. So it will actually react to the frequency of the driving field. Okay, so what you see here is an amplitude that doesn't oscillate with the intrinsic frequency, but with the frequency of the driving field. And this is, if you have a harmonic oscillator, if you push it off resonantly, okay, it will react to the frequency of the driving field. And then you also see we have this denominator. Okay, so we have the difference, the detuning, and we have this decay rate, and this whole thing. You also just see if I log it out. No, it comes later. Okay, so we have a resonance behavior. If I drive the system on resonance, okay, then this is gone, and then the response would be the effect is the largest. But even if I drive on resonance because I'm damped, okay, this whole system will not explode. Okay, it will not. When we discussed these coherent states, we looked at so if you without any damping, you plug in here resonance, then the amplitude will simply explode over time. But because there's a finite damping, we'll reach a finite value to put energy from outside. And this also dissipates energy. That will be a finite steady state. And you see this typical kind of, if you take the absolute value, you get the Lorentz curve with the detuning squared plus the width here squared. Yeah.
So if we didn't have the bar, so gamma would be 0, and we would drive the system at resonance, it would just like the cavity mode would just go to infinity.
Yeah.
It would just have more and more energy.
Yeah. So this is really a resonantly pumped system if you don't have any way to get rid of the energy. Yeah. So there's this typical resonance. Okay, so the response is the highest around the resonance frequency of the system. And then, of course, you see, I mean, how sensitive is it? Then it's essentially given by this decay rate. That's a typical Lorentzian line shape here. So then let's look at now also the photon number. Okay, so this is now a different expectation value, A dagger A. Okay, but I do the same type of trick here, same type of calculation. A dagger A, of course, commutes with the Baire rotation, with the Baire Hamiltonian, but it will be affected by this driving field. Okay, so we get from this commutator, so this is the driving part. And we have then this from the dissipation part. Okay, we have now these other type of commutators. So A dagger, commutator with A dagger A, and so on. So now again, you can evaluate these things, and do I do this? Now let's look at it on this slide. Okay, so evaluate this commutator. What does it give? Here I pull out the A dagger in front, and then what's left is an A dagger A, that gives me a -1. But then -1 times I have one A dagger and I have an A, so minus A dagger A expectation value. And similar for the other. So this guy gives essentially, okay, this A I can put out on this side, and this gives me again a -1, and I still have an A dagger A here and another A from the back. Okay, so this would give me 2 times minus A dagger A expectation value. And similar for the other line, so we can go through this. So these are the 2 things I just pointed out. Okay, minus A dagger A, minus A dagger A. There should be, of course, an overall expectation value around everything. And the other 2 terms give me an A dagger, but also 2 times. Okay, so now I see essentially I have the fact, okay, I have a minus sign. Okay, so this term and this term, they come with a different sign. But also you have to keep in mind here I have an A dagger A and here I have an A dagger. Okay, so before I subtract these 2 terms, I want to write A dagger as A dagger A plus 1. Okay, use the commutation relation. So therefore there will be some offset, a 1 here and a 1 here left. And the other 2 terms, they cancel again. Or almost cancel again. Okay, so what I have, this is my coherent part. And now I get, so the evolution of the occupation number, it decays with gamma. Okay, not gamma over 2. I mean, this makes sense. The amplitude decays with gamma over 2. And therefore, the amplitude squared, so the occupation number decays with gamma. Okay, so it's simply twice the rate. But I also now have from this factor over here, I have now this additional contribution gamma times n thermal. Okay, so for the occupation number, it matters whether I couple to a thermal reservoir or a 0 temperature reservoir. So so I mean with very briefly, so if I now take, okay, these things, they might still look a little bit scary because also now the expectation value of A dagger A depends on the expectation value of A that we had before. We can actually, so suppose for now that this last term is gone, okay, so occupation is gone, set this to 0, then it actually turns out that the expectation value A dagger A of T is simply the expectation value of A squared. And you can either verify it, put in the results from before into this expression and integrate it, or you can just, if you take this result and take the time the derivative here, work out the product rules, you find that this will then essentially reproduce these 2 results. Okay, so this means that, I mean, without proving it in all detail, but what we have found, so if I'm sitting at n thermal equals 0, we have a mean value of A that is exactly the same as the amplitude, the equation of the amplitude for coherent state. Okay, so if you really go back to these results that we had in the very beginning, and we also find that A dagger A is just this amplitude squared, and that's not a mathematical proof, but it kind of hints. Okay, I have a mean value. And the mean value is A dagger A is just the mean value squared. So that's the property of a coherent state. So from this type of expectation values, I mean, in principle, we would need to evaluate also higher orders and show that this property holds true for all orders. But in principle, we can say that for a driven dissipative cavity, if it's just driven by a classical driving field, I mean, we already had this proof that a system driven by a coherent system driven by a linear driving field produces coherent states. And this essentially tells you, even if I have now this decay included, all what I get if I drive a harmonic oscillator is a coherent state. Okay, but now we can also see the opposite, and just not to mess everything up. So let's take the opposite limit. What happens if it's not driven? And then I have an equation of this type. Okay, so derivative of A dagger A is minus gamma A dagger A. Okay, just decay, but also this offset term here. And in this case, I mean, you convince yourself. I mean, if I want to integrate it, okay, I play a little bit around or do an educated guess here. So what's happening? Okay, the evolution of eta A, so that if I'm initially in some value, this can be 0, but it can also be finite at the initial time. And then this initial part simply decays, okay, because I've decayed to the environment. So I lose the information about the initial occupation number. But then as time progresses, I have so 1 minus this quantity in the initial time, this is 0. But for large times, this becomes 0. So I just have 1 times n thermal. So at very long times, the occupation number here now settles to the correct value of the thermal equilibrium number. So we have also here a relaxation equilibrium. So suppose we would have the cavity initially in the ground state. Okay, then it would go up. And the time scale that it goes up, I mean, is proportional now to this gamma. Okay, it's not enhanced. It's just a gamma time scale. If I'm initially in a very high number of photons already, then I would decay. And eventually, for large times, I would relax to the thermal equilibrium. So also here we see that actually this master equation that we've written down is kind of consistent with our requirement, that the coupling, if I couple something weakly to a thermal reservoir, it should itself reach a thermal equilibrium state on a long time scale. So now, and yeah, I think I will actually stop. So maybe now, of course, you can complain and say, okay, I mean, there can be many different, can also construct your coherent state that has the same occupation number, okay, and this will not be a thermal equilibrium state. So at this stage, we only have information about the average photon number in the cavity, but the photons can still be distributed arbitrarily over all the number states. Okay, so at this stage, we haven't proven that it's really a thermal state. And so therefore, we need to go now one step further. But actually, I think this I will continue then next week. Yeah, okay, so then let's stop here.